Welcome, everyone. I'm excited to kick off our presentation today with the topic of database CO and CPTS. This is the first slide, so I want to warmly welcome you all and thank you for being here. Today, we'll explore the fundamental ideas behind databases, including their structure, function, and importance. We'll cover key concepts that form the foundation of understanding how databases work and why they're so essential in today's data-driven world. So, let's get started and dive into the fascinating world of databases. Let's take a closer look at the contents of this presentation. We start with the concept of a database, which is at the core of managing data effectively. Moving on, we see the importance of understanding why we need a database management system, or DBMS, because it helps us organize, store, and retrieve data efficiently. Next, we look at the components that make up a table within a database. Understanding these components is essential for designing and working with data structures properly. We also explore the file system, which is the traditional way of handling data before databases became prevalent, and why moving to a DBMS offers significant advantages. Following that, we delve into key concepts in a DBMS, which include how data is stored, manipulated, and managed securely. Then, we examine the relational data model, the most common approach used today, and why it's so powerful for representing real-world data. As we progress, we focus on the various terminologies used in the relational model, which are crucial for understanding how data relates and interacts within the system. We also highlight the different types of keys in a relational database, such as primary keys, foreign keys, and others, which are fundamental for maintaining data integrity. Finally, we discuss referential integrity, a key principle ensuring that relationships between tables remain consistent, which is vital for accurate and reliable data management. Throughout this presentation, our goal is to build a solid understanding of how databases work, why they are essential, and how key concepts like keys and integrity ensure the database functions smoothly. Let's talk about databases. So, a database is essentially a collection of interrelated data, meaning the data is connected in meaningful ways to each other. This setup allows it to serve multiple applications simultaneously, making it a very versatile tool. Think of it as a computer-based record-keeping system. It's designed to store information efficiently. But what's really important is that it doesn't just hold data. It also allows us to modify or update that data as our needs change. This flexibility is key to managing information effectively and ensures that the database can adapt to different requirements over time. Connecting this to our overall theme, understanding databases is fundamental because they form the backbone of how we organize, access, and manipulate information in various systems. Let's talk about the file system, which is a fundamental part of how data is stored and managed in a computer. A file can be thought of as a container that holds data, whether it's text, computer program code, or CSV files. These files are stored on the computer's storage device, like a hard drive or SSD. It's important to realize that files aren't limited to just text. They can also be images, audio or video clips, or even web pages. This variety highlights how versatile files are in representing different types of data. Now, once files are stored, they can be accessed directly, which means you can open and view the data they contain. However, to efficiently find specific information within these files, especially if they are large, you often need to write computer programs. These programs help search and retrieve data quickly, making data management much smoother. This connects to the overall theme of understanding how computers organize and access information efficiently. Knowing about files and their management is crucial for effective data handling in any computing environment. Let's take a closer look at what a DBMS is. DBMS stands for Database Management System, which is essentially a software that helps us handle data efficiently. It allows us to create, store, manipulate, maintain, and retrieve data from a database. This is useful whether you're a user or an application program. Think of the DBMS as a bridge. It connects the database itself with the end users or applications, making data access smooth and controlled. It simplifies complex data operations and ensures data integrity. there are many examples out there, ranging from open-source options like MySQL and PostgreSQL to commercial solutions like Oracle, SQL Server, and Microsoft Access. For NoSQL databases, MongoDB is a popular choice. Understanding the role of a DBMS is fundamental, as it supports data management across various applications, tying into our overall theme of efficient data handling and system design. When the number of files increases and the volume of data grows, managing them with a traditional file system can become quite challenging. That's where a database management system, or DBMS, really shines. One of its key advantages is that it reduces redundancy. Redundancy means having the same data duplicated across different files, which can lead to inconsistencies and wasted space. A DBMS stores data in one central location, so all applications refer to that single source, making data management much more efficient. Another important point is that a DBMS helps control inconsistency. When the same data exists in multiple places, it can get out of sync, leading to errors. By minimizing redundancy, the DBMS ensures that everyone is working with the same, consistent data, which improves reliability. Finally, a significant benefit is that it facilitates sharing data. Data stored in a database can be accessed and shared by multiple users simultaneously, which enhances collaboration and productivity. Overall, these advantages highlight why transitioning from traditional file handling to a DBMS is so essential as data grows in size and complexity. Let's talk about why a DBMS is so essential. First, it ensures security by protecting data against both accidental and intentional disclosures. That means whether someone tries to access information without permission or accidentally modifies data, the database has safeguards in place. Next, maintaining data integrity is crucial. A DBMS enforces specific integrity rules, which help guarantee that the data remains valid and correct over time. This consistency is vital for reliable decision-making and operations. Finally, a DBMS enforces standards in how data is organized and stored. By maintaining data in a consistent format, it makes it much easier to exchange or migrate data between different systems, ensuring compatibility and smooth integration. So overall, the need for a DBMS stems from these core functions: security, integrity, and standardization, all of which are fundamental to effective data management. Now, let's look at some key concepts in a database management system. First up is the database schema. Think of the schema as the blueprint or the design of the database. It's also known as the visual or logical architecture because it shows us how data is organized and structured within the database. This is crucial because understanding the schema helps us see the overall layout and relationships of the data. Next, we have data constraints. These are rules or limitations imposed on the data to make sure everything stays valid and consistent. For example, constraints can prevent invalid entries or ensure that certain fields always have data. They help maintain the integrity of the database, which is vital for reliable data management. Finally, we come to metadata or the data dictionary. This is where the database schema and all the constraints are stored by the DBMS. It's often called the database catalog or dictionary. Essentially, metadata is data about the data. It describes the structure, constraints, and organization of the database itself. This makes it easier to manage and understand how the data is stored and maintained, tying everything back to the overall goal of efficient, organized data management. Now, let's look at some key concepts in a DBMS. First, we have the database instance. Think of this as the current snapshot or the state of the database at any specific moment. It's like taking a picture of the database's data at a particular point in time. Next, we have data manipulation. This involves changing the data within the database, and there are three main operations here: insertion, deletion, and updating. These are the fundamental ways we modify data to keep it accurate and relevant. Moving on, a database query is essentially a request you make to the database to retrieve information. It's how we ask the database to give us the data we need, formatted in a way that's useful for us. And finally, the database engine. This is the core component or set of programs that power the entire DBMS. It handles the processing of queries, ensures data integrity, and manages the overall operation of the database. All of these concepts are interconnected. They form the foundation that allows a database to be dynamic, responsive, and reliable. Key themes as we explore how databases support various applications. In a relational database model, data is organized into tables, which you might also hear called relations. Think of each table as a grid made up of rows and columns. Each row in a table represents a relationship among a set of related values, almost like a record of a specific entity. The columns, on the other hand, represent the attributes or fields that describe aspects of that entity. For example, if we're storing details about students, the columns might include roll number, class, and section. Each of these columns holds specific information related to the student. When you gather all the data in a particular column across all students, that forms a set of attribute values. And each complete row, containing all the attribute data for one student, represents a specific instance or record. This structure helps us organize data clearly and logically, making it easier to manage and retrieve information efficiently as we build more complex databases. Let's take a closer look at the components that make up a table. First, we have the data item, which is the smallest unit of named data. Think of it as a single piece of information, like a person's name or a date. It's often called a field or a column in a table, and it represents one specific type of data. Next, there's the record. A record is essentially a collection of these data items that together represent a complete unit of information. For example, a record for a customer might include their name, address, and phone number, all the data items that belong to that one customer. Finally, we have the table itself, which is a collection of all the rows and columns, so all the records and their associated data items. It provides a structured way to organize, store, and view large amounts of data. Understanding these components helps us see how data is structured and managed within a database, which is fundamental as we move forward in exploring how data is stored and utilized effectively. Let's talk about some commonly used terminologies in the relational data model. The relational model was actually developed by ELCAAS at IBM back in 1970, and it remains the most widely used database model today. One of the key concepts is the relation, or what we often call a table. Think of it as a structure arranged in rows and columns, similar to a spreadsheet. Now, a relation or table has some important properties to keep in mind. First, all items within a single column are homogeneous, meaning they all share the same data type, like all integers or all dates. This consistency is crucial for data integrity and ease of analysis. Second, each column in the table is assigned a unique name. This helps us identify and reference specific data points easily. And third, the values in each column are atomic, meaning they are indivisible. For example, a single cell shouldn't contain multiple pieces of data bundled together. It should be a single atomic value. Understanding these properties helps us appreciate how relational databases organize data efficiently and consistently, which is fundamental to designing and managing effective data systems. Let's take a closer look at some of the key terminologies we use in the relational data model. First, it's important to remember that no attribute can have many data values within a single tuple. This means each attribute in a row holds just one value, keeping the data clear and consistent. Next, all rows in a relation are distinct, so you won't find two identical rows. They're unique, which helps us avoid confusion or data redundancy. Also, the order of the rows or the columns doesn't matter. Whether you change the sequence, the data remains the same, emphasizing the logical structure over physical arrangement. Another crucial point is the use of a special value called null. Null is used to indicate that a certain value is either unknown or not applicable to a particular attribute. This allows us to handle missing or inapplicable data gracefully without disrupting the integrity of our dataset. Connecting all these points, These terminologies help us maintain data integrity and clarity in the relational model, which is fundamental as we build reliable and efficient databases. Let's take a closer look at some of the most commonly used terminologies in the relational data model. First, we have the concept of a domain. This refers to the set of values that an attribute can take within each row of a table. Typically, we specify the domain using a data type, which helps ensure data consistency and integrity. Next is the degree of a relation. This is simply the number of attributes, or columns, in a relation or table. Think of it as the width of your table. Moving on, we have the term tuple, also known as an entity or record. Every row in a table is called a tuple, representing a single data entity or instance. Then there's the concept of cardinality. This refers to the number of tuples, or rows, present in a relation. It indicates how many records are stored within a particular table. Finally, we have attributes or fields. These are the individual columns in a relation, and they're often called fields as well. They define the kind of data stored in each column. Understanding these key terminologies helps us better grasp how relational databases organize and manage data efficiently within the overall data model. Now let's take a closer look at this table. Here, we have a simple example of a student database table, which is a fundamental concept in database design. The table is titled Student, and it contains several key components. First, there are the columns or attributes, which are the different pieces of information we store about each student. In this case, the columns are roll, name, and class. The roll number uniquely identifies each student. The name is the student's name, and the class indicates which grade or class they belong to. Each row in the table, called a tuple or record, represents a single student's data. For example, the first row shows that student VIJTHA has roll number 1 and belongs to class 12. This table structure helps us organize data efficiently and retrieve information quickly. It illustrates the core idea of a database table or relation, where data is stored in rows and columns. Understanding these components is essential because they form the foundation of how we manage and manipulate data in databases. So, in summary, this slide highlights the basic building blocks of a database table: columns, rows, and records, and how they work together to store organized data. When we talk about keys in a relational database, the first thing to understand is that each tuple, or row, within a relation must be unique. This means no two rows should have the same values across all attributes. In other words, there has to be at least one attribute where the data is different. This attribute is what allows us to distinguish each tuple uniquely. It's really about ensuring that each record can be identified without confusion. This requirement leads to some important restrictions or constraints on the data itself. These constraints help maintain the integrity of the data and also define how one relation can refer to data in another relation. These are the keys we use to enforce those rules. In essence, the concept of keys is central to the relational model because they ensure data uniqueness and integrity, which are fundamental to organizing and managing data effectively. This is how we keep our data reliable and easily accessible within the overall structure of the database. Now, let's talk about keys in a relational database, starting with the primary key. A primary key is essentially a set of one or more attributes that can uniquely identify a record within a table. Think of it as the unique identifier for each row. It's important to note that there can only be one primary key in a table, which helps maintain clarity and consistency. The primary key must accept only distinct, non-duplicate values, meaning no two records can have the same key value. Additionally, it cannot be left blank, because every record needs a way to be uniquely identified. Examples of primary keys include student ID number, student admission number, or Aadhaar card number, since each of these is unique to an individual. Recognizing and properly implementing the primary key is fundamental to organizing and retrieving data efficiently in a relational database. When we talk about keys in a relational database, one important concept is the candidate key. A table can have one or more attributes that consistently hold unique values for each row. These attributes are what we call candidate keys because they can each uniquely identify every tuple in the table. Now, Among these candidate keys, we choose one to be the primary key. The primary key is essentially the main identifier for the records in that table. It's also important to note that a table can have multiple candidate keys, but it will always have only one primary key. This primary key is what we rely on most for establishing relationships and ensuring data integrity across the database. Understanding candidate keys and the primary key helps us design more robust and reliable databases, which ties into our overall goal of creating efficient, well-structured data systems. Now, looking at this table, we can see several columns: stud ID, roll no, name, stream, and email ID. These columns are crucial because they help us identify individual students uniquely. In database terminology, such columns are called candidate keys. Specifically, in this example, stud ID, roll no, and email ID can each uniquely identify a single row in the table. For instance, if I tell you a student's stud ID, you can find all their other details easily. The same goes for roll no or email ID. This means these columns are candidates for the primary key, but usually we choose just one to be the main identifier. The key point here is that candidate keys are those that can uniquely identify data entries, helping us maintain data integrity. Understanding candidate keys is essential because they form the foundation of relational databases, ensuring that each record is distinct and easily retrievable. This concept ties into our overall theme of designing efficient and reliable data systems. Let's take a look at this table showing different classes, sections, and their total strength. Notice that the Class X has Section A with 32 students, and Class XII has 2 sections, A with 30 students and B with 28 students. Now, moving on to the concept of keys in a relational database, one important idea is the primary key. Sometimes, a single attribute isn't enough to uniquely identify each row in a table. For example, if you only look at the class or only at the section, you can't be sure which specific student or record you're referring to. That's where a composite primary key comes in. It involves combining multiple attributes to create a unique identifier for each record. In this case, combining class and section, that is, using both class and section together, forms a composite primary key. This combined key ensures that each row is unique, even if either attribute alone isn't sufficient. So the key takeaway here is that when a single attribute can't uniquely identify each record, we can use a composite key, which is a combination of 2 or more attributes. This concept is fundamental in designing reliable and efficient databases, especially as part of the overall data organization strategy. Now, let's talk about alternate keys in a relational database. As you know, in each table, we have multiple candidate keys. These are the sets of columns that can uniquely identify each row. Out of these, only one is chosen as the primary key, which is the main identifier for the table. The remaining candidate keys are called alternate keys. Essentially, an alternate key is any candidate key that is not selected as the primary key. For example, in the student table we discussed earlier, if stud ID is chosen as the primary key, then roll no and email ID become the alternate keys. They still uniquely identify a student, but they aren't used as the main identifier. This distinction helps us understand the different ways data can be uniquely identified within a table, and it's important for maintaining data integrity and flexibility in our database design. Now, let's talk about the concept of a foreign key in a relational database. A foreign key is used to establish a relationship between 2 tables. Essentially, it's an attribute in one table that refers to the primary key of another table. Think of it as a link that connects related data across different tables. What's important to remember is that the foreign key isn't a key itself. It's a non-key attribute that depends on the primary key of the other table. When you enter data into the table with the foreign key, the database checks whether that value exists in the primary key column of the related table. If the value is present, then the data entry is allowed to go through. But if it isn't, the database will reject the entry. This check helps maintain the integrity and consistency of the data across the database. So, in summary, Foreign keys are crucial for maintaining relationships between tables and ensuring that the data remains accurate and reliable throughout the database. They help enforce referential integrity, which is a key part of designing a robust relational database system. Now, let's talk about keys in a relational database. In some cases, a foreign key can actually take a null value. This happens when the foreign key isn't part of the primary key in the foreign table. So, it's important to understand that the table containing the foreign key is called the child table, and the table that contains the candidate key, meaning the key that the foreign key references, is known as the referenced or parent table. This relationship is fundamental because it helps us understand how tables connect and how data integrity is maintained across the database. Recognizing these roles and conditions allows us to design more flexible and accurate relational models. Now, looking at these tables, we can see that the CUSDAD column in the orders table is actually referencing the CUSDAD in the customer table. In other words, the CUSDAD in the orders table is a foreign key, and its value depends on the primary key CUSDAD in the customer table. Think of it like a link between the child table, which is orders, and the parent table, which is customer. This relationship helps us understand how data is connected across different tables in a relational database, ensuring consistency and referential integrity. So, whenever we see a foreign key, remember it's basically a way to connect related data from different tables, maintaining the overall structure of our database. Now, let's talk about referential integrity, which is a fundamental property of relational databases. Essentially, it ensures that any entry in a foreign key column must correspond to an existing primary key value in the related table. This means you can't insert a record with a foreign key that doesn't match a primary key somewhere else in the database. It also protects data consistency by preventing accidental deletions or modifications of related data that could lead to orphan records. For referential integrity to work properly, a few conditions need to be met. First, the master tables column should be a primary key or have a unique index. This guarantees each entry is uniquely identifiable. Second, the related fields in both tables must have the same data type, ensuring compatibility. And lastly, both tables involved must belong to the same database. Otherwise, maintaining this relationship wouldn't be feasible. Understanding and applying referential integrity helps us keep our data accurate, consistent, and reliable, connecting back to our overall goal of effective database management. Now, let's talk about referential integrity and the rules we need to follow when enforcing it with a foreign key. First, it's important to understand that we can't enter a value in a child table that doesn't already exist in the master table's primary key column. This ensures that every foreign key value points to a valid record. However, there is an exception. Null values can be entered in the foreign key. This is useful in cases where the relationship is optional. Next, on the topic of deletions, if a record in the master table has a matching record in a related child table, we cannot delete that master record. This prevents orphaned records, which could cause data inconsistencies. Similarly, if there's a record in the child table linked to a master record, we can't modify or change the primary key value in the master table. Doing so would break the link and compromise data integrity. These rules are fundamental to maintaining the consistency and accuracy of our relational database, which ties directly into the overall theme of data integrity and proper database design.